So today we will deal with the topic of Zeeman effect. It is very important in atomic physics, which we will explain with the help of quantum mechanics. So what we have learned in previous lecture is nothing but the magnetic effect on an uh, atom, like the way we have discussed the magnetic moment described by the electron rotating in an orbit, which is known as the orbital magnetic moment, and which is connected by the orbital angular momentum L by the help of this equation, and the ratio of mu L by L is was known as the gyromagnetic ratio and given by E by 2m. So these are the relation which we will use in our present lecture, so that the explanation will be given. So let me explain the history behind the Zeeman effect. In 1895, okay, so in 1895, scientist Zeeman observed that the energy spectral lines emitted by the transition of the electrons, as because we know that from Bohr hypothesis that electrons are revolving in certain stationary orbits in which electrons can neither emit or absorb energy, but the transition of energy takes place between two energy states. That is, if the electron will transit from a higher energy level to a lower energy level, then energy is released in terms of h nu. Okay, where nu is the frequency of the light emitting in the radiation, in the form of radiation. So this was a Bohr's hypothesis. So Zeeman showed that in 1895, noticed that the while transition from higher energy state to lower energy state, the spectral lines which was observed for electron uh, was split into a number of fine spectral lines. When the atom is placed in an external magnetic field. So in the presence of external magnetic field, the energy spectral lines emitted during the transition is split up into a number of fine components, which was later known as the Zeeman components. Okay, the spectral lines of different frequencies. We will show this uh, after some time. Okay, let me explain first what we have learned yesterday, that when the atom is placed, it consists of magnetic moment mu. Let us suppose this is oriented with some angle uh, with respect to some external magnetic field B as theta. Now the in the presence of the external magnetic field, this magnetic moment will try to reduce its energy, so that it will try to orient itself with the direction of external magnetic field, so as to reduce its potential energy. Now the torque acting on the system is given by mu b cross b with the help of magnetostatics. We know this very well, which can also be written as mu b b. uh, okay, wait a minute, this is not mu b, mu l, orbital magnetic moment. So mu l b, sorry, mu l b sine theta. What is the theta? Theta is the angle between the mu and b. So the torque acting on the system is given by tau equal to mu l b sine theta. Now the torque, from this relation we can easily find out that, name it as equation 1, we can easily find out that torque is maximum when theta is pi by 2. and torque is minimum when theta is 0. Okay, so the torque will be maximum in this position when when mu is when mu is perpendicular to B, and minimum when either mu is parallel or antiparallel with respect to B. Okay, so the potential energy, let us first calculate the work done. To determine the potential energy stored in the system, we have to do some work in deflecting the magnetic moment from the maximum value to certain angle theta. So the work done during this is given is stored as the potential energy in the system, and this is given by some du, which is nothing but tau d theta. Okay, so u, let me name it as um. This is the magnetic potential energy stored in the system. So um will be given by pi by 2 to some theta, tau is mu lb sine theta d theta. Okay, so if we integrate this system, then mu lb will be independent of theta, and this will be pi by 2 to theta sine theta d theta. Now we know this integration very well. Mu lb cos theta pi by 2 theta. So to absorb this negative sign, we have to uh, change the upper limit and lower limit, exchange the upper limit and lower limit. So cos theta theta pi by 2, then we will get minus mu lb cos theta. This minus sign have great significance as the potential energy must be tried to reduce, so this negative sign arises. So negative sign has great significance, so this can also be written as mu l dot b. Now if we so what we have done nothing but integration. Okay, so we obtain this result mu l dot b. Now um, if we consider only the magnitude, then this can also be written as mu lb cos theta. Okay, now from our previous discussion we know very well between the relationship of mu l and l. Let me copy this equation number 1 of my previous lecture. Okay, so from this we can write mu l is equal nothing but minus e by 2m. Okay, if we take only magnitude, then e by 2m into l, this will be put on this. Okay, if we put the value of mu l in this equation, then we will get that um is equal nothing but e by 2m bl cos theta. Okay, now cos theta. From our previous discussion, we also can obtain the space quantization concept. From the space quantization concept, yes, the cos theta is nothing but, let me copy this also. This, or it can also be written as Lz by L. So if we put this cos theta as E by 2m BL, Lz by L, LL will be cancelled out. So E by 2m B into Lz. Now the eigenvalue of Lz can also be written as E by 2m B into ml H line. Now this EB by 2m has some special name. What is this? If you have forgotten it, then please see the previous lecture. All the terms I have introduced in my previous lecture already. So this is nothing but Bohr magneton, which I am going to show you. Where? Please wait. EP by 2m. Um, okay. Bohr magneton have introduced here by the relation EH line by 2m. Just a minute. EH line by 2m. So Bohr magneton can be given by EH line by 2m. So if we substitute this by the help of Bohr magneton, then E by 2m can also be written as mu b by H line, this E by 2m, and this will also be present. So this H line will be cancelled out, and this will become mu b ml into b. Okay. So this is the magnetic energy what we have obtained. This is the required magnetic energy what we have obtained. So this is an additional energy. What is this? This is the additional energy what we have obtained when the atom is placed in some external magnetic field. External magnetic field. So this is the additional term. So the actual energy or the final energy now becomes the initial energy plus some mu b into ml and b. So the final energy, so the difference between these two energies, EF minus EI, which was previously given by h nu is not equal to only h nu, is equal to some h nu with an additional of mu b ml into b. So it depends as well as on ml. Okay, so if we write this, uh, mm, let us consider that the initial energy can be given by h nu naught and the final energy given by uh, uh, okay, let us denote this the initial energy released. So energy exchange when the magnetic field was absent. So when the magnetic field was absent, this was the difference in energy. And now when the magnetic field is present, this is the energy difference, which is equal to the sum of the previous one as well as another quantity. Okay, so let us explain this, and this as h nu, this will become h nu. So if we put this value, then h nu will be obtained by h nu naught plus mu b ml b. Okay, so the new frequency now becomes nu is equals some nu naught plus mu b b upon h into some ml. So this is the final expression. Now we know very well that for given L, what is L? L is the orbital angular momentum quantum number. For given L, we have 2L plus 1 values of ml. Let us suppose for L is equal 1, the value of ml becomes minus L 2 plus L steps to unity. So ml becomes minus 1 0 1. So for given 1 values of L, we can get ml is equal 2 into 1 plus 1, that is 3 values. Okay, for L equal to 1 we have 3 ml values. If there are 3 ml values, then this frequency will also divide it to some 3 values of frequency. So either it becomes nu naught mu b b upon h line h into some 12 plus 1 component. If L be 1, then M will be ML can also have minus 1 0 1. So this can be for plus 1, this can be for uh, M0 ML0, and this will be for this can also be for minus 1. Okay, and you can also imagine that For L equal to 2, ml is minus 2 minus 1, ml will be minus 2 minus 1 0 1 2. Then this frequency will also divided to some 5 component, but this will not possible as because of selection rule. All the combination of energy state, that is all the transitions, are not allowed. We know it very well from the quantum mechanical concepts, selection rule. So all the transition are not allowed. What transition are allowed is given by some selection rule. So now we will consider the selection rule. Selection rule. What is the selection rule for ml? Selection rule for ml is ml can delta ml can be plus minus 1 or 0. So the transition will takes place for the difference of ml, in which the difference of ml is either plus 1 or minus 1 or 0. If the difference between 2 ml values be suppose minus 2 and 0, there is a difference of 2 or minus 2, what you can say 2 or minus 2, this transition is not allowed. Whereas minus 1 to 0 is allowed, minus 1 to 1 is allowed, minus 2 to 2 is allowed, but minus 2 to 0 is not allowed, 2 to 0 is not allowed, but minus 2 to minus 1 is allowed. Okay, so these are the selection rule for ml. So this is true for selection rule. So this is possible for delta ml plus 1. This is possible for delta ml delta ml 0. This is possible for delta ml minus 1. So these are the frequency components. Applying the selection rule, we can also we can easily obtain this. Now to summarize this, let us write what we have learned here. Okay, so what we have learned here, let us summarize it as: thus the uh, energy of a particular atomic state depends on okay, thus we here noticed that the energy of a particular atomic state depends on the value of ml as well, on the value of initial energy difference. Okay, so a state of orbital angular momentum quantum number L can split into 2L plus 1 states. Okay, depending on the value of depending on depending on depending on email. Okay, so that differs in energy mu b into b. Okay, this phenomenon of phenomenon of splitting of energy spectral lines into fine components or substates, subcomponents on application of external magnetic field is known as Zeeman effect. Now you may think that why I have left this space, as because what we have learned here is known as normal Zeeman effect. This is not the complete story regarding Zeeman effect, as because before the concept of spin, it was assumed that only angular momentum of electron is present. uh, from the Schrodinger equation, you know that from the Schrodinger equation we can only get the concept regarding orbital motion, not the spin motion of electron. So we here assumes that orbital angular momentum. So it is also true for the case where the spin gets cancel out each other. So for the paired electron system, okay, this is also true for the paired electron system where the spin gets where there is a up spin and down spin, so that the spin effect gets cancel out. Okay, so this is not the complete story regarding Zeeman effect. This is known as the normal Zeeman effect, which is due to the orbital motion of electron only, where we have considered only the orbital angular momentum and orbital magnetic moment of electron. Let me explain this with the diagram, with a simple diagram. Okay, let us take the transition between L equal to 2 and L equal to 1. Suppose this is L equal to 2 and this is L equal to 1. Now before the application of magnetic field, we can only obtain the transition of this with the frequency h nu naught. Okay, but this can also split up on the application of magnetic field. This can also assumes to be split out into 2. So this can also split up into 12 plus 1. Here L equal to 2, so 5 components. So this can also split up into 5 components. Okay, and this can also split up into 3 components. Please draw this carefully, otherwise the diagram will be dirty and will be very difficult to notice. Okay, this is for the ml value, let us say 2. This is for ml value 1. This is for ml value 0. This is for ml value uh, -1. This is ml value -2. This is for ml value +1, ml value 0, ml value -1. Now in the selection rule I have forgotten to write some uh, another selection rule, that delta L should be uh, 1. Delta L is equal 0, that is same L transition is not possible. This I have forgotten to say. Okay. Now what I told you in selection rule, selection rule for L is worked out here. So selection rule of ML is going to apply here. Selection rule for ML, delta ML is equal ±1 and 0. So the transition can takes place from 2 to 1, uh, 2 to 1. Okay, so -2. Okay, 2 to 1, 1 from 0, and 0 to -1. For finding the delta ML, you can subtract the initial value from the final ML, initial value of ML from final ML. So this I have drawn for ML 1 minus 2, that is -1. This I have done for -1. Now it important point here to notice that although there are three spectral lines, but these are for the same delta ML. So delta ML, for delta ML equal to -1, we get the three components. So in the frequency band we observe only one spectral line, although here we notice that there are three transitions, but we can only notice one spectral line in the spectrometer graph, as because these are possible only for one delta ml value. So this is important point to notice. Now okay, let us move on. So 1 to 1, these lines should be straight line. Here digitally it is difficult to draw the straight line. but I am trying to make the graph very clean and clear. So like this, the spectral line should be straight, 0 to 0 and -1 to -1. So these three spectral lines are due to delta ml is 0. Again, the selection rule, we have used the selection rule delta ml 0, delta ml -1, but delta ml plus 1 is left. So 0 to +1, -1 to 0, and -2 to -1. Now these are due to delta ml plus 1. So if we simply here see, then this will be for undeflected spectral line, only one spectral line was present. But for when we apply, here you have to write, when we apply magnetic field, magnetic field, the spectral line becomes this, this, this. Why I have noticed, why I have plotted the some spectral line in upward direction and some in lower direction? This will be explained with the help of polarization. So after studying polarization, you may explain this. So if you want to take the explanation of polarization of this, then I will try to explain you. So let me write. Quantum mechanics leads not only to the selection rule but also to the polarization rule. For observation of uh, for observation at right angles to the magnetic field, the transition of delta ml is equal 0 is results in spectral line polarized with electric vector parallel to the field, electric vector parallel to the field. Okay, these originates by component, whereas for delta ml plus minus 1 transition results in lines polarized with the electric vector perpendicular to the field. These are known as sigma component. So what we have plotted here, this is pi component and these are sigma component. These are for delta ml minus 1, this is for delta ml plus 1, and this is for delta ml 0. So the whole story given in this lecture is regarding the normal Zeeman effect. And what is the Zeeman effect actually? So let me revise. In 1896, scientist Zeeman observed that the spectral lines emitted during the transition of the from higher energy state to lower energy state is split up into the some components into a number of components on the application of external magnetic field. This was known as Zeeman effect, which cannot be uh, explained with the help of Bohr's model of theory. So Bohr's model have disadvantage, or Bohr's model have some limitation regarding the explanation of the Zeeman effect, but the actual explanation was given later with the help of application of Schrodinger theory. Schrodinger's wave equation, we can obtain we can solve the hydrogen atom problem and we get the radial equation as well as orbital angular momentum. We have obtained some orbital angular momentum, magnetic moment on the application of external magnetic field. So this was solely dependent on the angular magnetic moment and angular orbital angular momentum. So when spin is also employed, then we will uh, use the JJ coupling or LS coupling. That is, the spin orbit interaction will be taken under consideration, and the theory is some more complicated a little bit from the normal Zeeman effect. So this will be explained in upcoming lectures. Thank you very much for watching. Okay.